Hello, everyone. My name is Megan Ellsworth here at RoofersCoffeeShop.com, and you are watching a Lunch and Learn today brought to you by Johns Manville. I'm really excited because we're talking about one of the most important design elements in a building, and that is the vapor barrier. And Johns Manville y'all are experts at this. So I'm excited to discuss this. And Jacob, you are my guest today. Can you introduce yourself?
Yeah, thanks, Megan. So my name is Jacob Heaps. I'm a product manager here at Johns Manville. I've been with JM in the roofing business for about 9 years now. I've been a My role as a product manager at JM is to essentially make sure that our product offerings meet our customer demands, and we have all the various system components that customers or designers might need to make a high performing roofing system.
Absolutely. Absolutely. And I love when I get to do webinars with you all because I live in Denver and I live like a mile from the JM Tower downtown Denver. And it's just so fun to get to hang out with my friends. So, yay. Um, okay, so we have three learning objectives for our Lunch and Learn today. And the first one is understanding the science behind vapor barriers. Then, second, we're going to talk about identifying when and where vapor barriers are needed. And lastly, we're going to explore Johns Manville's vapor barrier solutions and installation methods and talk about kind of the nitty gritty details of it. Um, so first, Jacob, let's get into understanding the science behind vapor barriers. Can you kind of explain how vapor barriers move moisture through the roof and out?
Yeah, I think a lot of it comes down to I think most folks, including myself, fell asleep during high school physics class, right? But it comes down to the physics, right? A building is almost a living kind of a living structure in some regards, right? It's you have air moving through, you have temperature changes throughout the year. So it's really driven by like the second vapor drive is driven by the second law of thermodynamics, right? Which says that air is naturally going to move from warm, moist environments to cold, dry environments, right? And so, kind of based on different buildings, different geographies, where they might be in the country, and then obviously what season it is outside. It's something that definitely needs to be considered, especially in colder climates, right? Whenever all that warm, moist air is on the interior of the building, and then the outside's cold and dry. That's where you really start to see the impact of vapor drive. But again, I think that's only one example of where vapor barriers or vapor retarders can be a benefit from a roofing system perspective.
Okay. And I mean, since we're in Denver, that's huge. During the winter, it's super cold and dry outside and warm and moist inside.
Yep, exactly. Yeah, I think the Northeast is always Northeast, Midwest, right? Anywhere you get those cold, dry winters and warm summers, right? That's really where you see, I think, different dynamics within the building envelope, depending on the season throughout the year.
Got it. So, can you kind of define, relative humidity, dew point, and vapor pressure?
Yeah, most folks, right? You turn on the evening news, or you check your iPhone app today, right? Probably more common. You see, they'll give the weather, and then they'll also give a relative humidity and a dew point, right? And I think most folks directionally kind of know what that means, right? High humidity means it's going to be sticky, right? But really, so relative humidity is actually measured as a percentage, right? And that is actually measuring the amount of free water vapor that's in the air, right? So, completely saturated, which is very uncommon, 100% humidity. If there was absolutely no water vapor in the air, it'd be 0% humidity. And then on the flip side, the dew point actually kind of goes along with that relative humidity, right? So you have this water vapor in a gas form in the air. The dew point indicates, what temperature that water vapor is going to condense back to a liquid, right? So, if you ever spent any time in the south, like the southern part of the United States in the summer, right? Generally, you'll come out the next morning and your car's got a bunch of condensation on the windshield. That kind of vibes with gives you a good real world example of how those two work together, right? You have a high relative humidity percentage in the summertime in the southern United States. You have a dew point that tends to fall kind of in that 60, 70 degrees when it gets cool at night, and that leads to that condensation on different surfaces. And then the vapor pressure differential really kind of looks at the building, right? So I think relative humidity and dew point are kind of not unique to the building envelope. Vapor pressure differential actually looks at the temperature and pressure deltas that are commonly throughout the life of the building, right? There's differentials between the interior and the exterior, and so that temperature and pressure delta kind of causes that vapor drive, right? Going back to the differentials and, where that vapor is going to move at a given time throughout the year.
Got it. Got it. Oh my gosh. I didn't realize I'd be getting a weather lesson. This is awesome. So how do you identify, can you kind of identify how condensation forms and affects the performance specifically related to, the roofs and keeping that moisture moving through the system?
Yeah, I think, there's a couple of different things. I think starting at the construction phase, right? There's a lot of people, a very common way to stagger or stage a construction schedule, right, is to get the building dried in with the roofing system, right? So the contractor will go up there and put down the roofing system, dry the building in, and that allows the remainder of the interior to be completed then and not have to worry about, the effects of weather throughout the course of the construction schedule. But what a lot of people don't realize is, that there's a lot of construction generated moisture being generated throughout the construction process, right? So if you actually enclose a building and then you come in and pour something like a concrete floor slab, or the different workers might have heaters going if it's a colder season, right? Those are generating usually propane gas is what's being used to run those heaters that has moisture that comes out of it. And then there's obviously paints and flooring and all these other types of interior type products that might be used. And those can actually all kind of generate moisture. So even if you aren't in I'd say a cold, one of those areas that I talked about that has those cold, dry winters, some people kind of just say, okay, we don't need a vapor retarder or vapor barrier. But, I think the construction is one aspect that should be considered to make sure that, hey, you might not think you need one long term, but it could be a benefit throughout the construction schedule based on kind of how things are lined out.
Just asking a follow-up question on that. Would you say that, I mean, vapor barriers are kind of important anywhere, not just like you said, where it's cold and dry outside and warm inside?
Yeah, I think it's value engineering is so common, right? But I think it's almost like a design benefit, right? And so, the choice to use a vapor barrier, it shouldn't really come from the contractor, right? It should be coming from the designer on a specific job. And they should be the ones that kind of look at, the building location and then some of these other things like, the potential for construction generated moisture. And really, it's like, my 2 cents is always, adding one in generally is going to be a benefit, right? So if there is an opportunity to use it, right, it just can lead to long-term benefits from energy efficiency, and then just an additional layer of protection, I guess you could say, for the interior build of the building. Yep. So apart from construction, right? I think there's building the building use is another key thing to use, right? Because I think looking at the interior humidity, I talked about that's that percentage that measures the amount of water vapor in the air. Some buildings have naturally higher amounts of humidity just based on what they're being used for. So a couple examples would be like baking facilities, right? Obviously, a lot of moisture being generated in the baking process. Museums tend to have relatively high humidity interior humidities to make sure that things don't degrade if they're showing artifacts or things like that could be impacted by dryness. Gymnasiums and high schools, things like that, right? You have a lot of sweaty teenagers. Yeah, yeah. Pools is another one, obviously very high humidity in an indoor pool environment. So again, I think there's a number of different reasons why you might want to use a vapor barrier, just depending on kind of the building, the construction schedule, all those things. And then the last one is probably the substrate. So, structural concrete roof decks are fairly common in some parts of the country, right? They obviously, areas like Florida, very high wind loads are needed where concrete decks do really well versus something like a steel deck, or lightweight insulating concrete is very popular down there as well. So again, those naturally throughout the curing process of the concretes have water added to them, right? And that water has to evaporate out eventually. And so, again, that's another very common use to utilize a vapor retarder if you have those types of underlying substrates.
Oh, okay, that's huge. That's wow. Okay, I didn't even think of that. The water has to go somewhere, right?
Yeah, exactly.
Okay, so well, this is already, I'm learning so much. This is fabulous. So, our second learning objective is identifying when and where vapor barriers are needed. And we've kind of touched on this, but let's get really into the nitty gritty. So, can we talk about the CRREL and NRCA guidance for climate and humidity guidelines?
Yeah. So I think, the number one question that we get on the manufacturer side a lot from designers is, do I need it or not? Right. And I think, everyone looks for that, one size fits all answer. And I think there's there's really not a one size fits all answer with any building or any roofing system, I think, right? There's always a lot of factors to consider. So there's a couple guidelines out there that I think designers can use, right? The first is the CRREL, like you mentioned, is the U.S. Army Corps of Engineers Cold Regions Research and Engineering Lab. It's a little bit. That's probably it's one of the older methods I would say to evaluate. But really, what that looks at is the interior relative humidity percentage of your building, right? So again, if you are designing something like a pool, that's naturally going to have a higher interior relative humidity. Most commonly, most people find comfort between like 30 and 50% relative humidity inside an interior of a normal building, you could say. And so yeah, so the U.S. Army Corps' map basically lays out I call them squiggly lines, right? But barriers across the geography of the United States, and says, hey, if your interior, it's got numbers that kind of as you go further and further south increase, and so it says that if your interior relative humidity of your building is going to be above this in this certain geographic location, you might want to consider it, right? So that's kind of the oldest one. I think it's a quick one stop. And what you'll find is that 50% humidity kind of falls right along the central part of the United States, kind of cuts, right across Missouri, Illinois, northern Kentucky, southern Indiana, that sort of area. So really, the Midwest and the Northeast are the two major population areas that fall into that. The NRCA came out with a little bit clearer guidance, I think, right? They use the ASHRAE climate zones, which are very commonly used for all things building envelope. I would say most designers are very familiar with those climate zones, and so they said that if you were in the 6A, the 7, or the 8 climate zone, which really is kind of the extreme northern United States, or very very cold winter areas, that's where you should always use one. And then they kind of gave a little bit more guidance around temperature in January and the indoor relative humidity. So again, I think that's probably the easiest thing for most designers to remember, which is that if the average outdoor temperature for the geography of your building is less than or equal to 40 degrees Fahrenheit, and the indoor relative humidity is greater than 45%, you're probably going to benefit from using a vapor retarder in that system. So, like I said, those are the two probably most common quick stop, I'd say, areas that designers can look at. But again, there's a number of ways you can kind of attack it on an individualized basis as well, for depending on your building, which is you can conduct a dew point analysis, which actually looks at where is that dew point going to fall with if throughout the year. And ultimately, what you're trying to do is avoid that dew point falling within your roofing system, because I mentioned earlier that dew point is where the water vapor recondenses into a liquid, which is what everyone's trying to avoid within the roofing system. And so, yeah, you can actually conduct, looking at the specific roof system, the amount of insulation that's being used. You can conduct a more specific, I'd say, analysis on your given building.
Interesting. Okay. Wow, I'm learning so much. So we talked about kind of recognizing the building types that require vapor protection, like concrete and all that sort of stuff. Can we kind of dive into that a little bit more? What are some, you know, common building types that you would say would always require vapor protection?
Yeah, I kind of hit on them earlier, right? I think, any sort of pool, if there's an indoor pool, right, that's one. A gymnasium is another. Baking facilities are the other one, right? And again, those are probably the most common that we see, but I would say it's definitely not all inclusive. And I think that the takeaway is really just kind of understanding what's the building going to be used for. Is there going to be a lot of interior water vapor being generated, and then utilizing? I think, and one thing for designers to consider that sometimes gets missed is, what's the long-term potential use of the building, right? They, yeah, so you might be designing a building for one use today, but long term the owner might want to utilize it for something else, right? So I think that's a question that designers sometimes miss, or I think it's worth value in terms of just asking the question to the building owner or their client around, hey, is there going to be a potential change of use long term? Because that's again a way you can build in an additional layer of protection at the initial construction phase versus having to go back and deal with problems down the road if there is a change of use.
That's such a good point. So let's talk about the differentiation between class one, two, and three vapor retarders.
Yeah, so I think, vapor barriers is kind of thrown around in the roofing industry. But really, if you look at the IBC or International Building Code, right, they're actually defined as vapor retarders, right? And so essentially what that is, it just means that it's a material that will reduce the rate at which water can move or water vapor can move through it. So within that, they have three different classes, like you mentioned. So class one, which again, the IBC those are what everyone in the industry refers to as vapor barriers. Those are going to be quote unquote impermeable, right? So there's an ASTM test method that looks at the ability of that water vapor to move through a material. The measurement that comes out of that test is called a perm or a perm rating. So to be considered class one, you have to be less than or equal to zero point 0.1 perms, which essentially means that for all intents and purposes, no water vapor is moving through it. So, all roofing membranes, right? We all know you put the roofing membrane down, it protects your building from, exterior precipitation, rain, whatever it might be. You're not getting you're not getting water vapor moving through those roofing membranes, ideally, right? So all roofing membranes would fall into that. A couple other commonly used products that would be class one in the industry are going to be like self-adhesive SBS sheets that they'll have a polyethylene facer on top, or a 6 mil polyethylene is commonly used in the industry as well. Some people will call it visqueen. So again, it's those are probably the two most common things you see. And then class two and class three are just a little bit more permeable, right? So they let a little bit more water vapor through. So those can be beneficial in certain areas where there might be a need to get water out of a system, right, or out of a given cavity or building or whatever it might be. So on the low slope side, you don't see it, but these are definitely prevalent on I say residential construction, right, steep slope, things like that. And so again, it just all comes down to how much water vapor passes through a material based on that testing that's done that spits out that perm rating.
Yeah. And this might be a silly question, but how does mold um, get involved? Like, how does that relate to maybe like a class two, three vapor retarder like that?
Yeah, so that could be, there's, and again, this kind of looks at the not just sort of the roof system, but the overarching building envelope, right? There's definitely concerns. 'Cause I think the watch out is, if you do trap moisture between two impermeable, substrates or two impermeable membranes per se, that's a risk that can happen is that, mold can start to develop because, that humid air or that water vapor is going to be sitting in an enclosed space. It has nowhere it can evaporate out to. Um, and so yeah, so I think that's definitely prevalent in like the wall side of things, right? So whether it's insulation or house wrap or whatever it might be. So again, that's not necessarily low slope, but yeah, it's a risk if a designer was to improperly specify or a contractor was going to use the wrong type of material in a given area. So.
Got it. Okay, and then class three.
Yeah, those are really going to be semi-permeable, right? So again, that would be a good example of house wrap on a residential construction. Concrete blocks are probably a good example of those as well, right? They'll slow water going through it, right? But it's not going to stop it per se. It'll eventually evaporate out through the concrete pores. So.
Okay, awesome. Well, okay, we're on to the third learning objective already. It's gone so fast. So, exploring Johns Manville's vapor barrier solutions and installation methods. So, we're going to kind of talk about the methods you all, implore to install these. So, can we compare the self-adhered and the vented system designs that you all have?
Yeah, so I think the most commonly used product that we see here at JM are going to be like self-adhesive asphaltic based products, right? And so those essentially will use an SPS asphalt adhesive. Like I said, they'll be topped with a woven film generally to help with that perm rating. And so we have two solutions there. We have JM Vapor Barrier SA, which is a non-reinforced solution, very very similar to a number of other products on the market. And then JM Vapor Barrier SAR is a little bit more robust version of that. So it incorporates a fiberglass reinforcement just for additional strength and durability. A lot of folks will utilize vapor retarders for temporary weather protection. So we've found that additional glass mat, a little bit of extra thickness, right, creates a more robust solution. And obviously, there's a lot of benefits to these products, starting mainly with the installation technique, right? So they're self-adhering, so they come with a release liner on the bottom side, very easy to install for contractors, right? Very easy to train new people on the roof who might not be as familiar with different installation techniques. Very very quick installation, and then again you end up with a nice kind of uniform surface there at the end of the day. And then the other benefit is utilizing that SBS asphalt, right? There's actually an ASTM test method that comes from residential underlayments that looks at the ability of products to self-seal around a fastener, right? So, with shingles, obviously you're driving nails into the underlayments there, and the test method looks at, okay, let's say it's been penetrated. Does it still block water from getting into that hole that's essentially been created below the fastener? And so, a lot of polyiso will be mechanically fastened in a low slope system, and so that SBS asphalt it just kind of reseals around those fasteners to ensure that you don't have gaps for potential water vapor to flow through. And again, kind of proven out by the ASTM test method that comes from the residential side. And then, yeah, I mean, again, I'd say those are our two most common kind of vapor barrier products that are designed to be vapor barriers, but a lot of contractors or designers will use other just standard SBS sheets, right? So, Dynagrip base SDSA is one of our SBS base sheets that utilizes the same self-adhering installation. It's a little bit more robust of a product as well. So, again, there's a number of those options out there. I'd say that just kind of depends on what the designer's looking at or what they prefer in their given system.
Love it. Okay, so um, let's. I would love to understand some of the installation methods and performance benefits for some of these systems as well. Let's go a little bit deeper into that, and just to wrap this whole thing up.
Yeah. So I think I talked about the self-adhesive SPSs, right? And there's a couple new types of products coming to market more recently, I'd say. So a lot of that comes down to factory mutual or FM requirements on given buildings. So some buildings require or are going to be FM insured, so you have to have an approved FM system. And so the asphalt products have historically struggled with. If you were going to go direct to a steel deck with those. And so you would have to incorporate usually a thermal barrier below that, which obviously adds labor, adds material costs for the contractor. So, utilizing the same self-adhesive installation method, most manufacturers are kind of looking at, can we make a different product that allows us to cut out that thermal barrier? And so, again, I think you're seeing a bunch of new products coming to market. And again, the big benefit is generally the fact that you can get that FM Class 1 direct to a steel deck approval without the need for a thermal barrier. So again, I think a lot of cool stuff coming to the market, right? In the last couple months and in the future months here from different manufacturers. So again, I think it's going to provide benefit to contractors at the end of the day because it just helps speed up that installation process, make sure that that you're not going to have to add additional labor for material and stuff. That's really just driven by a code requirement. So, here at JM, we looked at it and said, hey, let's develop a solution that works for everyone, meets the code, and improves the installation time for contractors.
I love it. I love how you all do that, and I mean, your R&D department is just like insane. You're going nonstop, constantly innovating. It's so cool to see all the stuff that you all are constantly coming out with, and trying to help your contractors and your customers be ahead of the curve. I think that's so brilliant.
Yep. Yeah, and you hit on vented systems, right? I think that's speaking of R&D, right? We had a new product come to market about 3 years ago called Dynaset 1K. And I talked about, the major benefit of this product was it comes down from I talked about concrete and lightweight insulating concrete, obviously having moisture in it. And so the traditional way that you would kind of adhere to those would be, with hot 2 plies of glass that were hot mopped down, right? We all know that, that's kind of becoming less and less common throughout the country. Hot asphalt application is a little bit, I don't say frowned upon, but it comes with some drawbacks like odor and fire risk and all those things. And I think just contractor familiarity, right? There's less and less contractors who own a kettle and have crews that are trained to install that. So again, Dynaset 1K allows you basically to adhere a vapor barrier down to a concrete deck or a lightweight insulating concrete deck, and it's a moisture cure adhesive, and so you can actually put it down in ribbons. Those ribbons allow any moisture that might be in the concrete or the lightweight concrete to basically move around underneath the vapor retarder and find a way to vent out. And then obviously being moisture curing, anytime there is moisture, it actually enhances the cure and gives it, a stronger performance. So again, I think that's just another example to your point around, our development team, our R&D teams looking at, what are the problems for designers and contractors and GCs out there today, and can we develop a product that alleviates some of those headaches?
Wow, that's so brilliant. Oh my gosh, that's so brilliant. And the fact that it enhances the cure as that vapor, that water is leaching out is so smart. Um, well, Jacob, thank you so much for teaching me about vapor barriers today. This lunch and learn was so educational. I hope everyone out there learned something and was taking notes. And please be sure everyone out there to do the test, the quiz, and fill out the handout because you can get entered to win a free lunch if you take the quiz. So please do that. And thank you, Johns Manville, for sponsoring this lunch and learn and just always bringing education to the forefront and helping contractors out and make sure they are on the forefront of the industry. So you guys are so great at that. So thank you, Jacob.
Yeah, and thanks for having me on, Megan. Like I said, we're happy to, provide education where we can. I know, there's new products coming out all the time, and it's tough to really know, hey, what's the value in it. So I think, things like this, right, vapor barriers or any type of new installation methods, right, things like that that make everyone's life easier should be broadcast as wide as we can. So
Yeah, I completely agree. And if people want to go check out everything JM has to offer, please go to their directory. You can find their website from there and see all of their products that they have and all the other webinars and lunch and learns that they've done with us. You have done so many. So, and then really quick, what is your website?
Yep. So jm.com, like you mentioned, right, it's got all of our, product data sheet, installation guides, educational modules, things like that that you can check out. Speaking directly on vapor barriers, we do have a JM vapor barrier field guide that kind of sums up most of what we talked about today, right? A lot of the common products, kind of gives a little bit more background on each of those, as well as, obviously the installation side. So yeah, so jm.com. And then, yeah, there's a commercial roofing section up top there that can lead you what you need. So.
Perfect. Well, Jacob, thank you so much for teaching me today. And everyone out there, I'll see you next time on the next Lunch and Learn.